All right, everyone. Sorry for the delay there. It is always awkward trying to run the Zoom meeting and record it at the same time. But what I'm going to be talking about for the next 45-ish minutes is priorhoods, likelihoods, posteriors, and all that. And I don't know how many people recognize it, but there's a very famous vector calculus book called Div Grad Curl and all that. So titles of that. It is based on, I mentioned this text yesterday, Probability Theory, The Logic of Science by E.T. James. I'll mention this again. This is actually, I've been looking a lot at this book over the last few weeks. This is a very confusing book. Don't start here, but as you progress through and become, experts or world experts in Bayesian inference, this is going to be a really fantastic resource where a lot of the really leading people have gotten their intuition, learned how to think about problems from. So just keep it in mind. This book, Statistics, Data Mining, and Machine Learning, again, it's a kind of go-to reference for most people, I think, in survey astronomy now. And it's much more accessible, and it's super applied, and it has code, and all sorts of great things to look at. And then this is also a very common recommendation, but Data Analysis of Bayesian Tutorial by Civia is a really fantastic short little book, and a lot of people teach out of it. So those were my references in putting this together. For an overview and my pedagogical strategy this afternoon, I'll talk about the role of prior distributions in Bayesian inference. I'll talk about some practical principles for assigning or picking prior distributions. I'll discuss the conditions under which the choice of prior can make a difference for your inference. And I'll also really heavily focus on why certain choices of distribution are common and you see repeatedly across many different contexts. My pedagogical strategy is to start with something that you know, study it closely, and then introduce some new takes on the same idea. We've seen this a lot today, and I think walking around the room, I think the language is starting to become very natural. But when I was first learning Bayesian inference, the language was very confusing. So I just wanted to remind everyone, Bayes' theorem is written that we have a posterior, which is the thing we're interested in. That's the thing on the left, and it's something like I have some parameter vector theta, and I infer that based on my data and some background knowledge I. People often drop the background knowledge I, but it's important to include it to remind yourself that anytime you're solving a problem, you have a lot of auxiliary assumptions that you're making that you may not specify explicitly, but they're still there, right? And those can be very simple statements like, I don't know, the world exists. That's a piece of background knowledge that you should account for in your inference. Or it could be something very specific, like our survey has surveyed 3,500 square degrees or something, right? We infer the posterior based on our likelihood, which is the probability of the data conditioned on some model. And we have some prior information, and this is really just specifying the explicitly important things from our background. The denominator of this is called the evidence, and a term that I just recently learned, which is a much more appropriate description for what the bottom actually is the fully marginalized likelihood. We will talk, I think, more about this throughout the week. It turns out for a lot of problems, you can kind of ignore it. It ends up just being a normalization for your inference, and I'll mention that a little bit more throughout this lecture. I sort of hinted at this just a second ago, but as scientists, our goal is to construct models of the world based on our observations. So our goal is, in my view, always to calculate posterior probabilities that our theories or hypotheses are true. I mentioned this just a second ago. Calculating the evidence with a fully marginalized likelihood is often a difficult computational task. We often don't need to actually do it because we can always normalize our distributions after we're done with our inference. But we have a significant problem, which is that we need to pick functional forms for our likelihood function and for how we're going to assign priors to our model parameters. The most common distribution is in all forms of inference, and I think you've seen this, is the Gaussian distribution. And people often overstate the confidence with which they've assumed a Gaussian distribution. So I want to talk about where Gaussians come from and I'll give you multiple proofs that the Gaussian is a common distribution, and then I'll ask you to prove some generic things as challenge problems in the problem section. And in those challenge problems, if you choose to pursue them, you can work through some of the conditions that have to hold for a Gaussian to be the appropriate choice of either prior or likelihood. So part one, the central or the Gaussian distribution. My favorite derivation, and the derivation that I used when I was teaching undergraduate laboratory classes for biology students, is very similar to one of the historically earliest derivations, which came from Herschel. What Herschel was trying to do is estimate the position of a star given some noise in both the x and the y directions. And so I'm assuming here some sort of flat sky approximation rather than working in angles. So there were a couple of premises that went into this. So the first is that the error in the x and the y direction must be independent, and that the probability of the star having some xy position is independent of the angle between x and y. These are just basically saying that the x and the y directions are somewhat symmetrical, right? That I can swap x and y and nothing has changed physically. There's coordinate labels that I get. Under those assumptions, my probability distribution function for the x and the y position factors has to factor in this way. It has to just be the product of the distributions in x and the distribution in y. And we can also write that just as well for coordinates. So because I've made this statement that this distribution has to be independent of the angle and polar coordinates, that means that it just depends on r. And so I can substitute in the definition of r in polar coordinates in terms of x and y. Then what I can do is I can say this thing factors. Let me just consider the x and the y components separately, and I'll do that by setting y equal to 0. And I'll go ahead and take a log of both sides, and this gives me this expression. For both of these sides to be equal, what that means is that f of x has to be some function like alpha x squared. And since I can do the same thing in the y direction, and accounting for the fact that I took a log at one point, I arrive at the Gaussian distribution. And this makes sense to us, right? We think the x and the y directions are independent of each other just naturally, and we also don't have any reason for thinking our errors would be asymmetric, right? It's kind of an intuitively minimal assumption for why something like a Gaussian distribution would be the correct likelihood, or the correct distribution for this problem. I'll also mention that this is called the Herschel-Maxwell derivation, because Maxwell used an almost identical argument to work out the velocity distributions in classical gases. So the next derivation that I'm going to give is not as obvious. It's much more recent. I think it's from the 20th century, and it concerns looking at noise distributions in an electrical circuit. But it has a kind of unique intuition that leads to Gaussians being a kind of thing you might assume happens in nature a lot. So suppose that the distribution of voltages in a circuit over some many measurements made at different times is not given by a single fixed distribution, but there's actually a hierarchy of distributions. Every time the voltage in the circuit changes, I'll get a new distribution, and we want to work out what functional form does that distribution have. So the hypothesis here is that that distribution will be the same functional form, just at a new location. As I shift my voltage V around, I'll just shift my distribution a little bit, but it'll have the same functional form. And that's the hypothesis that turns out to actually explain what we observed. So suppose that the difference between the new and the old voltage, as I shift around in this hierarchy, is given by just some little additional voltage. If I then consider what the new probability distribution must be, that must have to do with what the previous voltage distribution was, which is this, times some additional distribution over these little voltage changes. So the sum and product rules mean that the voltage distribution of the new voltage is equal to this interval. By looking at the probability axioms that we covered yesterday. I can then Taylor expand this thing. So doing the Taylor expansion, including the integrals here, for the distribution of the new voltage V prime. And then if I say that this is a zero mean process, so I'm equally likely to move up as down in my voltage offsets, what I can do is I can start dropping some terms. And what I arrive at is a diffusion equation for the voltage distribution. And the solution to this equation is a Gaussian. And so what we've shown is that my probability distribution for voltage, given some parameter sigma that describes the width of this distribution, is a Gaussian distribution. So if you were like me the first time I saw this was a lot of math. It was kind of confusing, wasn't super easy to follow. Don't worry about it. I'm including it because it's a really nice example of what actually happens in nature, which is a bunch of little things happen in an additive way. And when you add all of those things up, you get a special distribution, which is the Gaussian distribution. And that's the whole point here. This is just a common way to frame problems that leads to the Gaussian as being an intuitive outcome. And this is what a lot of people sort of appeal to when they select a Gaussian likelihood in the absence of some other principle that they're using to select their likelihood function. There was going to be a part 1C. There was going to be a lot more confusing arguments like the one I just gave. But historically, it's important, so I've left this as a challenge problem. But Gauss's original derivation is based on a principle you see a lot in the derivations of distributions in, I don't want to call it theoretical statistics, but in the kind of hardcore statistics literature, you see arguments like this. What Gauss said is he said that the maximum likelihood estimate has to be the arithmetic mean. And it turns out that this statement uniquely picks out the Gaussian distribution. And again, I walk you through that argument in the problem section notebook. This resolved a historical argument where people were confused as to whether when you make a bunch of measurements, errors would tend to cancel or add. People thought that if you make a bunch of measurements with errors, that you get progressively less certain about what the outcome is. And it turns out that you can show from this kind of statement that errors will tend to cancel. And this allowed theory to catch up with experimentalists who sort of already knew this. This was originally worked out in inferring the orbit, I think of, I want to say Neptune, not 100% sure, but it had to do with measuring orbits. And prior to this being worked out, people were really uncertain about the orbit because they thought the errors on the measurements of the position were adding rather than canceling. Okay, I'm going to also talk about the central limit theorem, which is a statement that a lot of people appeal to in justifying the choice of Gaussian. Actually, before I put the definition up, is anyone willing to tell me what the central limit theorem is and what it says? Okay. Why don't you all talk about what you think the central limit theorem says, and then we'll see if somebody's more confident and wants to venture a guess.
A good form if you sum
But like we get okay. No, they were like basically
yeah.
Okay. So I said,
Let's chat for about 30 more seconds. The room goes completely silent. Is anyone willing to venture a guess about the central limit theorem and what its formal statement might be? That's fine. Yeah, no, go ahead.
So if you have some sort of X expected value for an experiment, the more times you perform the experiment and graph out your measurements, when n becomes very large, then your values converge to the value that you expect.
Yeah, that's pretty close. It's a little bit more formal, but that's really good intuition. And that's the intuition that people use often in selecting a Gaussian distribution. I'm going to put the statement up. This is the statement in the frequentist interpretation, and I find it very cryptic. And what I'll ask you to do is I'll ask you to prove this in a way that's more intuitive from the Bayesian perspective. But it's important to know that this exists. The simple limit theorem says that if I have a large number of random samples drawn from some population that has a mean and a variance, then the sample mean of the first n samples has a limiting form where this quantity is normally distributed. So that doesn't seem obviously useful, but it's one of the core results in sort of the frequentist interpretation. Right? So this is a good thing to look at. Yes.
What is it? If by saying you're sampling from something with a mean variance, does that imply Gaussian?
That is a good question. Looks like you have thoughts on it.
Yeah, so I remember the initial distribution of the population base is not can be basically that's not each of the
Right. And so there are actually many central limit theorems. What this is saying is that it has to have a mean and a variance. It could have higher order moments, right? So the Gaussian, we'll talk more about this. The Gaussian is picked out basically by saying, right, specifying information about the mean and the variance specifically, but it could be some higher order distribution. And there are many distributions that will you sample from that will could converge to a normal distribution as you take more samples. Right? So the point here is that this is a kind of confusing result. I'm going to give you a different perspective that I think is more intuitive in the problem section. And I had something else I wanted to say. I'll come back to it. Okay. So we talked a lot about this yesterday, which is the notion of picking a uniform or an uninformative prior. So one of the things that I was reading this morning was kind of maybe a little bit snarky, in that it pointed out that one of the reasons why a uniform or an uninformative prior seems like the right choice is because people are uncomfortable often with the notion of strong priors, right? We think we're scientists, we want to be driven by the data, we don't want to tell the data what the answer is, and so we think if we pick an uninformative prior, we're making we're putting the least subjectivity into our analysis. And so that's one interpretation of the uninformative prior. A formal way to sort of say put the least information in is something called the principle of indifference, which I think we also talked about yesterday. And that basically said, I just want to assign the same probability to every option that I have to consider. And this can be justified based on sort of imagining that you shift everything over and you want the answer to be the same. A uniform distribution will do that. However, if you look, and we'll talk about this in a specific example very briefly, if you actually look at sort of classes of transformations that you could apply to your parameters, what it turns out is that for scale parameters, like the width of the Gaussian, the uniform distribution is actually a distribution 1 over that parameter, or a uniform distribution of the log of that parameter. So to give an example that I think was a little bit controversial in the room yesterday, and you've now seen the line fitting example, I think, a lot over the last 24 hours. What I put up yesterday was this statement about probability transformations of probability distributions. And so we're going to go ahead and employ this to look at what the appropriate uninformative prior will be based on how I parameterize my line fitting problem. Let's consider 2 ways. So in the first case, we do what we've done, which is we write something like y equals alpha plus beta x, and I want to infer alpha and beta. In the second case, I'm going to phrase the problem a little bit differently. I'm going to fit instead for x equals alpha prime plus beta prime y. And what I can do is I can consider two prior distributions in alpha and beta, and alpha prime and beta prime, and I'll denote those P and Q respectively. So we can write our distributions from the definitions of these parameters. We can work out how they're related, and we can apply our probability transformation rule to work out in the new parameters how the original distribution is, or an equation that relates the original distribution to the distribution that we're looking for in terms of transform versions of those parameters. I apologize, the language here is a little bit confusing, the notation gets confusing. I'm happy to chat through this or answer questions about it. However, what you find is you get an equation that looks like this, and the appropriate probability distribution function that obeys this relationship has this particular form. And let me see, I put it here, which means that a uniform prior on the slope of a line is actually a uniform prior on the sine of the angle that a line makes with the x-axis, not a uniform prior on the angle itself. Okay, so DJ talked about this. When you make a uniform prior, when you assign a uniform prior on the slope, you are actually making a strong statement on what you think the angle is. And this is related to how we've defined the intercept in the way that we formalize this problem. And so we also include information about the angle in our definition of the intercept parameter, or the parameter that we intuitively think of as the intercept. We can create uniform priors on both parameters, but now we have non-uniform priors on our original parameters. And so what it turns out is sort of generically, a uniform prior is not always going to be a uniform prior on everything you tell. Okay, so when does the choice of a prior matter? So this is a really nice example. This comes from Civia's book in the small data limit. So it's probably a little hard to see. I put the notebook on the GitHub if you need to take a look at this figure. But what's happening here is as you go down, you are adding more point flip data, and you're trying to infer the biasing factor of a trick coin. And so what this plot does is it has a number of prior distributions, and as you get more and more data, independent of your prior, you converge to the same place. So if you're working with a very small amount of data, your prior is going to matter more. But once you have, say 128 or 1,000 point flips that you're measuring, the prior no longer has a large effect on your posterior distribution for the biasing factor. I think that's intuitive. Yeah.
Is there a way to define like the small data? Sometimes take it.
I don't know. Adam, so the question is there a way to sort of define when the small data limit is? I don't know off the top of my head. I might have forgotten if there's a formal criteria or formal test to see if you're in the small data. I think a lot of times you do, you simulate the problem, you see how the likelihood. I'll talk about how to do this in a second, but you want to sort of see what effect your prior and likelihood are having on each other, sort of prior to doing your full influence. I think that's maybe the answer.
I don't know if like a specific use this theorem or this method, but definitely comparing the prior to the posterior will give you some sense of whether or not this is the case.
And I mean, actually, just as a practical example, this is an example of doing exactly that, right? Put in a bunch of different priors, simulate some data, and see what, yeah. The other time, and again, this is kind of obvious, I don't have a formal mathematical criteria to employ here, but the other time your choice of prior can matter is if the prior is modulating your posterior near the maximum length. So if you have some really weirdly shaped prior that's really strongly peaked right at some particular value near the maximum of the likelihood function, your posterior is going to look like your prior, right? You need a lot of data to overcome that. And so that's just kind of an intuitive thing to be aware of. Don't pick a really strong prior, because it's really hard if you have a really strong prior to update your model of the world, no matter what your likelihood function is, because your prior is so strong. Okay, so some examples from your research problems, and this figure is a little bit hard to interpret, so I'm just gonna, and they actually don't have a nice figure in the paper that that shows the effect. But this paper studies in part whether you use a uniform prior. This is trying to measure the positions of stars in the galaxy, and you could use a uniform prior to try and do that, or you could do a prior that is aware that the galaxy has some sort of spiral arm structure. And what this paper finds is that when you include your prior information about the spiral arm structure, your distance measurements to stars tends to prefer distances that align with the spiral arms. So whether you prefer the uniform prior or the spiral arm prior will change your galactic structure measurement. Another example, and I couldn't get these to display side by side, but this comes from Alex. I think this is Alex's most recent paper, right? Yeah, if you'd like to.
So this is very specific to so it's type of experiment. It's also got prior W and so here the different colors are how it's animated around the sample. See the next same data, different prior totally different. So colors from the data are the same. So they're at the same.
I think, in addition to the kind of interesting implication that your inference for W matters depends a lot on the prior. I think the other thing that this illustrates is how to handle this in a principled way, which is showing that the effect of the prior matters, right? Checking a bunch of different priors, checking a bunch of different model assumptions, and being very upfront that you have made some choices in considering the range of priors, consider the range of data sets, etc. And that's also something that comes up a lot is when you have some really complicated posterior distribution, it's often really important to show the entire posterior rather than trying to summarize your posterior with just a few, like a best fit estimate and some uncertainty. If you have some multimodal thing, you might be able to construct something that looks like a variance and quote that as your uncertainty, but that's not a good representation if you have like a strongly, three strong peaks in your data set or in your posterior route. A famous example of where this matters is parallax measurements, and I've given this to you as a problem to work through. And this was thanks to Adrian, who is, I guess, one of the guest lecturers, and he'll be here tomorrow. Okay, so I'll introduce a couple of advanced topics and then wrap up. So when the posterior has the same functional form as the prior, we call the prior a conjugate prior. Some common conjugate priors, the nice one, this is one of the reasons why the Gaussian comes up so often, is a Gaussian is conjugate to itself. There's a detail here that we can talk about offline, but you can have biased posterior estimates if you're estimating both the mean and variance in the data. For discrete problems, another famous example is the beta distribution is conjugate to the binomial likelihood, and the gamma distribution is conjugate to the Poisson distribution. So one common use, and again, this is a way to sort of test what's happening in your inference, is to use conjugate priors and get some data and see how the data is affecting your posterior, since the shape isn't going to change based on using your conjugate prior. Finally, and this is really important, this is what comes up a lot, and this is another justification for using the Gaussian distribution everywhere, is something called the principle of maximum entropy. So suppose that we're not completely ignorant about the values of some model parameters, but for example, we know some ratios, we don't know the parameters themselves. If we assign a uniform prior or an uninformative prior, we're in some sense being too conservative. We're not capturing everything that we actually know in our inference. But we don't want to go too far the other way and pick a prior that is too strongly peaked and it's going to bias our inference too much. So we have an optimization problem. In fact, the formal derivations here use Lagrange multipliers and optimization theory to do this. In the Bayesian interpretation of probability, we think of probabilities as uncertainties. And the best mathematical definition of a uncertainty comes from some work done by Claude Shannon in the 1940s. So similar to the probability axioms that we looked at yesterday, I just wanted to introduce where the sort of maximum entropy formalism is coming from without fully deriving it. And I will post, if you'd like, I can share the formal derivation of all this. We're going to make some assumptions. We're going to say that we can construct a map of our uncertainty from probability. We're going to assume that's a continuous map. What that means is that if I move a little bit in my map or in my function that maps uncertainties to probabilities, I'm not going to like become way more uncertain just because I've updated my probability a little bit. This is a big one. This is something that I think a lot of people kind of miss or they get exactly backwards. It's a little unintuitive sometimes. But there's a common sense notion that if I have few options, I should be more certain than if I have many options. And so this is a kind of defining a directionality to uncertainty measurements. And then the other big assumption is that it's going to be consistent if we have one way to calculate our uncertainty and another way to calculate our uncertainty, they have to get the same answer. And it turns out that especially premises 3 and 4 turn out to uniquely fix the form of our entropy expression, and it's k log n, which is a very famous equation. It looks like thermodynamic entropy. So this is called the Shannon entropy. I'm not going to work through it, but it's possible to extend this and fully generalize it to continuous data sets. The rest of this. So some facts. If you have a fixed mean and variance for your prior distribution, if you think you know those things, then the principle of maximum entropy will yield the Gaussian distribution as your best choice for a prior. That's the best balance between being uninformative and including what you think you already know. If you have an upper or lower bound on a parameter, for example, you know that flux measurements can't be negative, then the maximum entropy principle will yield an exponential distribution as your best prior distribution. So this allows you to derive other prior probability distributions in other situations where you might not be completely ignorant. And you know, there's a vast literature of maximum entropy priors. Okay, so that was all of the sort of new background material. So I believe I put the problem set in the GitHub, so you should all have it. It's going to be something like priors, likelihoods, and posteriors. No solutions will be the name of the document. And there's 4 problems in there that I'd like you to think through. One concerns sampling for high-dimensional problems. This is why self-driving cars are hard. You can create some giant model that will fit a lot of situations you encounter, but driving is a really high-dimensional problem. And so, how well can you actually do that? Right? There's an example where choices about your prior distribution matter. This is a parallax example. And then I also give you a very famous example where things are not Gaussian, and I ask you to derive that likelihood. And then the final part of the notebook considers the origin of Gaussianity, a Bayesian statement of the central limit theorem, and a bunch of other stuff. The latter parts I was really challenged by them. It took me like a couple of weeks to fully process them. So I don't expect you to go through the whole thing, but I did most of the work for you. So if you encounter it at some point, if you're curious about it, I think you can probably fill in the intermediate steps without too much adversity. Okay, are there any questions or yes?
You said just low bound. What's the scale?
That's a good question. I don't recall off the top of my head how you. I mean, usually, yeah. Let me get back to you. I can give a better answer. I just don't recall. I've never actually been in a situation like in research where I've used an exponential distribution as my prior. So. Are there any other questions? Is this a good, there's so much to think about, or is this a bad, we're so overwhelmed kind of a situation? All right. Yeah. I put together this notebook and this lecture with the intent that this was a bunch of things that I didn't see anyone ever talk about or derive. And I want you to have somewhere you can go to and see it done at least a little bit. So that was the intent. All right, so I will be around to help out on problems, and yeah, that's it. That's all I have.
There's not.